Today we're going through capacitors, and so the capacitor diagram or the symbol of a capacitor looks something like this, where you have two parallel plates like this, and if we were to draw a diagram, we would have a capacitor, which is two parallel plates again, and we'll have a positive side and we'll have a negative side, and in between we would have a dielectric like this, and we would have an electric field going from the positive to the negative like this. And the dielectric is an insulating material, and the capacitance of a capacitor is equal to C, which is equal to the charge it holds over the voltage across it. And the dielectrics, they increase the permittivity, and the permittivity is a measure of how difficult it is to generate an electric field in a certain material. And it's denoted something like epsilon like this. And there's different types of permittivity. So you have the relative permittivity, which is equal to the permittivity of the material over the permittivity of free space. So what happens in a capacitor when you apply a voltage across it? So say you have the two plates again, so a plate like this and a plate like this, and you have the dielectric in between them. And you have the molecules in a dielectric are polar molecules, so they would look something like this. And you have them something like this, where they all point in different directions when there is no charge applied. However, when you apply a charge, so say we draw another diagram, so you have a negative charge and a positive charge now, and now all these polar molecules, so let's draw the dielectric first. So all the dielectric molecules will line up at the same direction as the electric field, and this is called polarization. So now the capacitance can also be written as C is equal to the area of one plate times the permittivity of the dielectric all over the distance between the two plates. So if you have two plates that look something like this, you have one plate like this, and underneath you have another plate like this. The distance between them would be this. You have D. The area, if the area of the plates is the same, you have A as one of the areas, and the permittivity of the dielectric in between would be epsilon 1. And this formula can also be written as A, using the formula from before that we said, this one, the definition of epsilon. If we rearrange, we'll get epsilon naught times this is equal to epsilon 1. So we'll get epsilon naught times epsilon R all over D. And this is another formula for capacitance. Alright, so now let's move on to capacitors in series and parallel. So say if we have capacitors in series, we would have the capacitance of 1 over the capacitance of 1 over the capacitance of the second one, plus 1 over capacitance of the third, plus etc. is equal to the 1 over the capacitance of the total. And if we try to explain why this happens, so say if we draw a nice series diagram of capacitors, let's just draw 3 so far. This, we can say it's very similar to a really large capacitor with a very large distance. If we have something that adds up all the distances, so we have this distance plus this distance plus this distance, and then this is the same as having a really large distance like this. And that is why, because the capacitance we said was 1 over is proportional to over the distance. If you increase the distance, the capacitance will decrease. So that's why you have this formula here. And in parallel, you would have capacitance C1 plus C2 plus C3 plus etc. is equal to the C total. And why is this? If we can represent this, so we have three capacitors all in parallel, like this. 1, 2, 3, 1, 2, 3, like this. We can represent this capacitor as like all of the capacitors together as just a really large capacitor, like this. It has the same distance between the plates, but now it has larger plates. So the areas of each plate here, here, and here would all add up. So you would have basically the same as a really large capacitor. And if we look at the formula again, we said that C, the capacitance, is proportional to the area. So the larger the area, the larger the capacitance. So that's why you add them all up. Now let's look at the energy stored in capacitors. So say we're going to draw a graph of charge and potential difference in the x-axis, V. And this would be, if you increase the potential difference, you increase the charge stored in the capacitor. So you would get a linear correlation, so a straight line like this. And the area under this graph, so the area under this graph, we can say is equal to the energy stored in a capacitor. So E is the energy stored in the capacitor. And if we write an equation, we know that the charge at this point would be Q, and the potential difference will be V, so we'll get coordinates of VQ. So the height of the graph, so this height is V, and the length, the height is Q, the length is V. So to find the area under the triangle, we'll do a half QV, which is equal to the area. Now we can write this formula in different ways using the formula for capacitance, which is C is equal to Q over V. C is equal to Q over V. Using this, you can make new formulas. So we can rearrange to get Q is equal to CV. And if we rearrange, if we substitute the Q, we'll get CV times V is equal to E. So we'll get another formula, which is a half CV squared is equal to E. That's another formula we can say is of the energy of a capacitor. And one last formula we can do with the same equation. We can rearrange to get V the subject, so we'll get V is equal to Q over C. And if we substitute into V, we'll get Q over C, which is equal to a half Q squared over C is equal to E. This is another equation of the energy of a capacitor that we can get. Now let's move on to charging and discharging. So we would get formulas for charge, voltage, and current. So for charging, let's start with charging first. We would get a formula for charge. We would get Q is equal to Q naught, final value of the capacitance, of the charge in a capacitor. And then we would get brackets 1 minus e to the minus t over RC. This is one equation. Then we would have, for the potential difference, we would have V is equal to V naught, which is the final potential difference that we have. 1 minus e to the t minus t RC. So you get something like that for the potential difference. And for the current, you would actually start off with a high current. So you would get I is equal to I naught times e to the tc minus tc over RC, like this. So what would the graphs look like for each of these? So you would have, for the current, you would have something like this, where you would have Q over time, and when it's charging, you would have no current at the start, and it will slowly increase and reach up like this into a plateau, where it plateaus at Q naught, which is in our equation over here. And for potential difference, you would do something similar, or you would have V over time. And the graph will also plateau, something like this. And the value it plateaus to would be V naught. But for current now, you would have a different graph. You would have I and T, so this would be time. And the graph you would get, it would start off with a large current, which would be I naught, and then slowly plateau, because as you start to fill up the capacitor, the more charges in it, so the harder it is to flow charge into it, so the current would decrease. And the current it starts at is I naught. So this is for charging. So now for discharging, you would have something similar and different. So the equations for discharging are very similar to the current equation. So for charge, you would have Q is equal to Q naught e to the minus t over RC, and V is equal to V naught e to the minus t over RC, and I is the same as the other equation, so I is equal to minus t over RC. And for all of these equations, you can have the same graph, whether it's charge, potential difference, or current. All the graphs will look something like this, where this, if this is charge, this one would be Q naught, and this would be T for all of them, so this is a time graph. And if it's potential difference, then you would have V, this would be V naught over here. And if you had current, if you had I, you would have I naught over here. So this is all the same graph, but for difference. And it's the same graph for all of them, which decreases exponentially like this. Now, if you can see in all of these equations, you have this RC constant for all of them. And to understand what that is, this is called the time constant. So it can be written as T, like this, tau, is equal to RC. And this is so that if you have any value of, this could be either charge, potential difference, or current, is equal to the initial or the final is equal to -1 when this happens. This is when T is equal to tau, the time constant. So if you rearrange this equation here, you would get x over x naught is equal to 1 over e, which is the same as e to the -1. And you'll get something which is 0.37. So T is the time constant for which the time of the current, the potential difference of the charge falls. So x, any of these x falls to 37% when discharging. And also the time it takes to charge, to 63% when charging. Now let's go on to linearizing a graph to find the time constant. So say we have any graph x, this could be either q, v, or I, is equal to x naught e to the minus t over RC. And this is, remember, this is for discharging. And to linearize the graph, you can make it in terms of ln. So ln x is equal to ln x naught e to the minus t RC. And because of log rules, you have this negative over here. So this would become ln x is equal to ln x naught. And then you can take this out, minus t over RC, because of the minus that you have on the power. And the e and the ln will cancel out. Then you will have ln x is equal to 1 minus RC times t, you can leave it out like this, like a coefficient, plus x naught. And now this looks like y is equal to mx plus c, where t is x and this is y. So if you have a graph of ln x, which could be either ln q, ln v, or ln I, could be any of these, and you have a time t, the graph could look something like this, where the y-intercept is, if we compare, ln x naught, and the gradient would just be 1 over rc, minus 1 over rc. And this linearization, you can find out what rc is and what x naught is as well, using this linearization equation. So when a capacitor is just discharging, the amount of time to halve the amount of charge that it started with can be found using the same equation. Say we have x, or either it's the charge or the potential difference or the current. X is equal to x naught e to the minus t over rc. And if you substitute x as x naught times a half, we can find out the amount of time it takes to halve the value of x, or any of the v, q, or I. So you can divide by x naught on both sides. You have a half is equal to e minus t over rc. And then you can take ln's, ln a half is equal to minus t over rc. And then if you rearrange this whole equation, you will get, due to log rules, you'll get ln 1 minus ln 2, where ln 1 is 0. So you can get rid of this, and you'll get a minus ln 2. And then you can multiply by minus rc, which will leave a positive rc. So ln 2 rc is equal to t. So ln 2 is equal to 0.69, around 0.69 times rc, which is equal to t. So the time for it to half, or the voltage, the current, or the potential difference, is equal to 0.69 of the time constant rc, or you can write tau. And that's the end of capacitance. Thanks for watching.